It is the autumn of 1954. A young graduate student at Princeton University is sitting alone in a library carrel, surrounded by papers he has covered in calculations so dense that the margins have long since given out. He has been working on the same problem for months. His supervisor has told him, with the particular brand of encouraging impatience that only great physicists can manage, that the idea is either brilliant or completely wrong, and that the only way to find out which is to follow it further. The student's name is Hugh Everett III. He is 23 years old. He's about to describe a structure so large, so strange, and so philosophically destabilizing that decades would pass before the physics community would begin to take it seriously. He is not trying to invent a multiverse. He is trying to solve a problem so fundamental that it sits at the base of quantum mechanics, like a splinter nobody can extract: the measurement problem. The question of what actually happens when a quantum system, an electron, a photon, a particle in a superposition of states, is observed, and the mathematical fog of all its possibilities collapses, apparently instantaneously, into a single definite outcome. Every physicist working at the time accepts that this happens. Every physicist working at the time calculates it the same way. Almost none of them are comfortable with the explanation, because the explanation does not have one. The wave function collapses. When asked why or how or where the other possibilities go, the standard answer is stop asking and do the calculation. Everett cannot stop asking. What if, he writes in his notes, the wave function never collapses at all? What if every possible outcome of every quantum measurement is equally real? And what we call observation is not a process that destroys all the alternatives, but a process that divides reality into branches. One for each outcome, each branch as physical as every other, each containing observers who see exactly what they expect to see, none of them aware that the other branches exist. What if the universe is not one thing but everything? Simultaneously, all of it happening at once. The single timeline we experience, just one thin slice of a structure so vast it makes the observable universe look like a grain of sand. What if, in other words, the multiverse is not a speculation, but a mathematical necessity? Everett followed the calculation. The answer arrived, and the answer has been making physicists uncomfortable ever since. Before we go any further, tell me in the comments which version of reality you think you're in right now. I am not being philosophical. I want to know, are you somewhere warm or cold, morning or evening, coffee in hand or already finished for the day? Drop it below. I'm going to come back to why your answer is more significant than it sounds. And if this is your first time here, welcome. Subscribe and settle in. We are about to walk through the full architecture of the multiverse. Not one multiverse, but 4 distinct kinds, each one nested inside the next, each one larger and stranger than the last, until we reach a scale of reality that makes the word infinite sound like an understatement. The quantum splinter. To understand the multiverse, you have to understand what forced it into existence as a serious scientific idea. It was not enthusiasm for science fiction. It was not philosophical adventurism. It was a splinter. Quantum mechanics is the most precisely tested theory in the history of science. Its predictions have been confirmed to more decimal places than any other framework physicists have ever constructed. The anomalous magnetic moment of the electron, a measure of how the electron responds to a magnetic field. has been calculated using quantum field theory and measured experimentally to 11 decimal places of agreement. No other theory in any field of human inquiry has achieved anything approaching this level of accuracy. And yet, quantum mechanics, at the level of interpretation, at the level of what it is actually saying about the nature of reality, is a complete mess. The theory describes the state of any physical system using a mathematical object called the wave function. The wave function encodes not a single definite description of the system, but a superposition, a simultaneous overlay of all the possible states the system could be in, each weighted by a probability. Before a measurement is made, an electron does not have a definite position. It has a wave function that assigns a probability to every possible position simultaneously. When a measurement is made, the wave function collapses. The electron is found at one specific position. The other possibilities vanish, or appear to vanish, instantaneously, regardless of how far apart they were spread. This process, wave function collapse, is not described by the Schrödinger equation, the central equation of quantum mechanics. The Schrödinger equation describes smooth, continuous, deterministic evolution. Collapse is abrupt, discontinuous, and random. The two are incompatible. Quantum mechanics has two rules that contradict each other, and the standard response has always been to use whichever rule fits the situation and not look too closely at what happens at the boundary. Everett looked at the boundary. His proposal was that the Schrödinger equation is always correct, and collapse never happens. When an electron in a superposition of two possible positions is measured, the universe does not pick one and discard the other. The universe branches. In one branch, the electron is found at position A, and the observer who measured it sees A. In the other branch, the electron is found at position B, and the observer in that branch sees B. Both outcomes occur. Both observers are real. Both branches of the universe are equally physical, equally governed by the same laws of physics, equally populated with matter and energy, and, where appropriate, with people. This is the many worlds interpretation of quantum mechanics, and its implications cascade outward in every direction, every quantum event, every radioactive decay, every photon reflection or absorption, every particle interaction at every scale in every cubic centimeter of space, has multiple possible outcomes, and the many worlds interpretation says all of them happen, all the time, in branching parallel realities that diverge from each other at the moment of the split and never reconnect. The universe is not a single history. It is a tree of histories, branching at every quantum juncture, extending outward and forward and backward in time into a structure of incomprehensible complexity. The physicist Bryce DeWitt, who helped rescue Everett's idea from obscurity in the 1970s, described it with a directness that remains hard to argue with. Every quantum transition taking place in every star, in every galaxy, in every remote corner of the cosmos, is splitting our local world into copies of itself. The number of splits per second is not a large number in any ordinary sense. It is a number so vast that ordinary language breaks down attempting to describe it. And Everett was not doing this to be provocative. He was doing it because the mathematics left him no other choice. The level 1. Multiverse. More of the same. The many worlds interpretation describes one kind of multiverse. a quantum multiverse of branching histories. But it is not the only kind, and it is not the kind that physicists most readily accept. That honor goes to a multiverse so straightforward, so geometrically inevitable, that it requires nothing more exotic than the possibility that the universe is large, very large. The physicist Max Tegmark, who has done more than almost anyone to classify the different levels of multiverse and examine their physical basis, calls this the Level 1 multiverse. It arises not from quantum mechanics, but from simple geometry, and it requires exactly one assumption: that the universe extends beyond the boundary of what we can see. What we can see is called the observable universe. It is the sphere of space from which light has had time, in 13.8 billion years of cosmic history, to reach us. Its radius is roughly 46 billion light years. Everything within that sphere is, in principle, accessible to our telescopes. Everything outside it is not. Not because space ends there, but because light from those regions has not yet had time to make the journey. Beyond that boundary, space almost certainly continues. The observations we have of the large-scale structure of the universe, particularly the extraordinary flatness and uniformity revealed by the cosmic microwave background, are consistent with space extending far beyond our horizon, possibly without limit. If inflation occurred in the very early universe, and the evidence strongly suggests it did, then the total volume of space is at minimum staggeringly larger than the observable region, and may be infinite. Here is what an infinite flat universe implies. The number of possible distinct configurations of matter within any finite region of space is finite. Quantum mechanics places a limit, determined by the Bekenstein bound, on the amount of information that can be packed into any given volume. In the observable universe, the number of distinct quantum states is enormous but countable. Call it some specific number, n. In an infinite universe, any pattern that can occur will occur. Not might occur with some small probability. Will occur infinitely often because there is infinite space for it to occur in. Every possible arrangement of matter, including, with absolute mathematical certainty, arrangements identical to the one currently occupying your observable universe, will repeat. The distance to the nearest identical copy of the observable universe in a typical inflationary model is roughly 10 to the power of 10 to the power of 115 meters. That number has no name. It is too large for any name to be useful, but it is finite, and in an infinite universe, it is the distance to the nearest place that contains a copy of you. Reading these words, having these thoughts, in a room indistinguishable from the one you are in. Not a similar you, an identical you, the same atoms in the same arrangements, the same memories, the same decisions being made in the same sequence. The Level 1 multiverse requires no new physics. It requires no exotic mechanisms or untested theories. It requires only that the universe be large enough, and everything we currently know about cosmology suggests that it is. Part 3. The Level 2 Multiverse. Different Physi. The Level 2 Multiverse. Different physical laws. The second level of multiverse is larger than the first and requires slightly more theoretical infrastructure, though that infrastructure is itself well motivated and widely accepted. The inflation that solved the horizon problem and the flatness problem, the exponential expansion in the first tiny fraction of a second of the universe's history, turns out, in most of the models that describe it, to be self-perpetuating. This was noticed independently by Andrei Lind and Alexander Vilenkin in the early 1980s, and the idea became known as eternal inflation. Here is the mechanism. Inflation is driven by a quantum field, the inflaton field, existing in a high-energy state that generates an enormous repulsive pressure, causing space to expand exponentially. As the field rolls down from its high-energy state toward a lower energy minimum, inflation ends in that region and the energy is converted into the hot, dense plasma of the Big Bang. A universe like ours is born. But quantum fields fluctuate, and in some regions, quantum fluctuations push the inflaton field back up rather than letting it roll down. In those regions, inflation continues, and because the exponentially expanding inflating space grows faster than the non-inflating regions nucleate within it, the total volume of inflating space is always increasing. Inflation ends locally, in one bubble after another, producing universe after universe. But globally, inflation never ends. It is eternal. Each bubble that nucleates is a separate universe, a self-contained region with its own post-inflationary physics, expanding away from the others at rates that ensure they can never communicate. What separates them is not a wall, but the inflating space between them, expanding so rapidly that no signal could ever cross it. And crucially, the physical laws in each bubble need not be the same as ours. In string theory, the possible vacua, the possible ground states of the quantum fields that determine the constants of nature, number something in the vicinity of 10 to the power of 500. Each vacuum state corresponds to a different set of physical laws, different particle masses, different force strengths, different values of the cosmological constant, different numbers of stable atoms. The inflationary multiverse samples this landscape at random. Each nucleating bubble settles into whichever vacuum it lands in, and the physics of that bubble is determined by that landing. In most of those bubbles, the physics is hostile to complexity. The cosmological constant is too large. Space expands so fast that matter cannot clump into stars or galaxies. The forces are wrongly balanced. Protons are unstable, or electrons are so heavy that chemistry cannot happen. The vast majority of the bubble universe landscape is, by any measure we understand, sterile. In a small fraction, the values land in ranges that permit atoms, stars, planets, chemistry, and eventually observers. We are in one of those. Not because our bubble was specially selected, but because observers can only find themselves in bubbles where the physics permits their existence. The landscape is not designed, it is sampled. We see what we see because what we see is what selection permits. This is the anthropic principle, applied at cosmic scale. It is not universally accepted. Many physicists find it philosophically unsatisfying. The feeling that it explains everything by explaining nothing, that invoking a vast, unobservable landscape to account for the apparent fine-tuning of our constants is a sleight of hand rather than a solution. But it is a coherent position with serious defenders, and it is the natural consequence of eternal inflation combined with a landscape of possible vacua. The Level 2 multiverse contains not just different regions of space with the same laws, but different regions with genuinely different physical laws. Different numbers of dimensions, perhaps. Different particle species. Different forces, different constants that govern the entire structure of matter and energy. It is a structure so varied that our universe, with all its extraordinary complexity, all its 2 trillion galaxies and 10 to the 24th stars, is one instance among an incomprehensibly large collection of instances, most of which are dark and empty and dead. What fine-tuning actually means. Before going further, this is worth sitting with for a moment, because the fine-tuning of the universe's physical constants is often presented as an argument for design and occasionally dismissed as a coincidence, and neither of those responses does justice to how strange the situation actually is. The cosmological constant, the energy density of the vacuum, the quantity responsible for the accelerating expansion of space, has a measured value of approximately 10 to the minus 122 in natural units. Theoretical estimates based on quantum field theory predict it should be of order 1 in natural units. The discrepancy between the theoretical prediction and the measured value is 10 to the 122. That is not a small discrepancy. It is the largest discrepancy between theory and observation in the history of physics. It is so large that no conventional mechanism can account for it. The vacuum energy predicted by quantum field theory, if it were anywhere near its natural value, would cause space to expand so rapidly that matter would never have had the opportunity to form into galaxies or stars or anything else. The universe would be empty and dark and expanding at a rate that made clustering impossible. The measured value is small enough to allow structure, small enough for gravity to win locally against the expansion, small enough for galaxies to form and stars to ignite, and planets to condense around them, and chemistry to proceed on their surfaces for billions of years. If you draw the value of the cosmological constant on a number line running from its minimum possible value to its theoretical maximum, the observed value sits at a position so close to one end that you could spend your entire life looking for it on the number line without finding it. The probability of landing there at random is not small. It is, for practical purposes, 0. The same applies, to varying degrees, to the mass of the electron, the strength of the strong nuclear force, the ratio of the electromagnetic force to gravity, the mass difference between the proton and the neutron, the energy levels of the carbon nucleus. Change any of these by small fractions, and the universe becomes uninhabitable. No carbon, no stable atoms, no long-lived stars, no water, no chemistry, no us. The multiverse does not make this fine-tuning disappear. It relocates it. Instead of asking why our universe has these specific values, you ask why we find ourselves in the rare bubble that does. And the answer, that only in such bubbles can anyone ask, is logically valid. Whether it is physically satisfying is a different question, and one that has no agreed answer. What is not in question is the fine-tuning itself. The numbers are what they are. The universe we inhabit sits at a very specific, very narrow, very unusual point in the space of possible physical laws. Any honest account of what the multiverse is and why it was taken seriously by serious physicists has to begin with that fact. Back to Everett. The Level 3 multiverse. Now we return to Hugh Everett sitting in his Princeton Carrel in 1954, following the mathematics to its conclusion. The many worlds interpretation, what Tegmark calls the Level 3 multiverse, is, in a specific and important sense, different in character from the Level 1 and Level 2 multiverses. The Level 1 multiverse is just distant space. The Level 2 multiverse is space with different physics, separated by regions that will never stop expanding. Both of these are multiverses in the sense of being separate spatial regions, elsewhere, very far away, unreachable, but in principle, physically located somewhere. The Level 3 multiverse is not elsewhere in space, it is elsewhere in quantum mechanical Hilbert space, the abstract mathematical space of all possible quantum states of the universe. The other branches do not occupy different positions in physical space. They occupy different branches of the wave function, coexisting with this reality in the same space but in a quantum mechanical sense inaccessible to any observer within any given branch. This is the detail that makes the Level 3 multiverse so philosophically vertiginous. The branch in which you made a different choice this morning is not somewhere out there across an ocean of inflating space. It is in the many worlds picture, here, superimposed on this moment, in the same location, sharing the same space-time coordinates. It is inaccessible not because it is far away, but because quantum decoherence, the process by which quantum branches lose their ability to interfere with each other as they interact with increasing numbers of environmental particles, makes it effectively invisible. Everett submitted his doctoral thesis in 1957. The reception was chilly. John Wheeler, his supervisor, who had helped develop the theoretical framework for nuclear fission and would later coin the term wormhole, expressed genuine admiration for the mathematical structure and deep misgivings about its implications. Niels Bohr, the patriarch of the Copenhagen interpretation that Everett was implicitly challenging, was reportedly dismissive. The thesis was published in a shortened form, and Everett, disillusioned, feeling that his work had not been given a serious hearing, left academic physics entirely. He went to work as a defense analyst. He applied his skills in game theory and systems analysis to Cold War military problems. He was good at it. He was never, by his own account, happy about it. The many worlds interpretation was rescued from obscurity primarily by Bryce DeWitt in the late 1960s and 1970s, who gave it the name by which it is now known, and argued forcefully that Everett's approach was not just a philosophical reinterpretation of quantum mechanics, but the only one that took the mathematics seriously on its own terms. Today, surveys of physicists suggest that many worlds is the most popular single interpretation of quantum mechanics among those who work at the research frontier, though it falls short of a majority, and the debate continues with full force. Everett died in 1982, aged 51, having never seen his idea receive the recognition it would eventually attract. His daughter, in a note found after her own death in 1996, wrote that she wanted to be cremated and have her ashes thrown away, so that she could be in the same place as her father's. His ashes had been lost. In some branch of the Level 3 multiverse, he lived long enough to see it. He died knowing he was right. The interpretation carries his name in the footnotes of physics papers that number in the thousands. Whether that is consolation depends on whether those branches are real, and that is exactly the question. The Level 4 multiverse. All that is possible. Beyond the Level 3 multiverse of quantum branches, Tegmark proposes something that most physicists find either the deepest idea in the philosophy of science or a step too far: the Level 4 multiverse. The proposal begins with an observation about the relationship between mathematics and physics. Every physical theory we have ever developed is expressed in mathematical language. The standard model of particle physics is a set of equations. General relativity is a set of equations. Quantum mechanics is a set of equations. The extraordinary success of mathematics in describing physical reality, what the physicist Eugene Wigner called the unreasonable effectiveness of mathematics in the natural sciences, has never been satisfactorily explained. Why should the universe obey mathematical laws at all? Why should the structures of abstract mathematics, developed in many cases for purely aesthetic reasons by mathematicians with no interest in physics, turn out to describe the deepest workings of nature with uncanny precision? Tegmark's answer is that there is no mystery here, because the universe is not described by mathematics. The universe is mathematics. Physical reality and mathematical structure are identical. Existence and mathematical consistency are the same thing. If this is true, then every mathematically consistent structure exists, not as an abstract object in some Platonic realm, but as a physical reality. Our universe is one such structure, characterized by the specific equations of the standard model and general relativity. Other consistent mathematical structures with different equations, different symmetries, different numbers of spatial dimensions, different kinds of logic, are equally real. Not nearby in space, not in a different branch. Simply real in the same sense that our universe is. Real because reality is mathematical structure, and mathematical structure is reality. This is the Level 4 multiverse. It contains not just universes with different constants or different vacua in the string theory landscape or different quantum branches. It contains universes with different mathematics. Universes governed by completely different kinds of logic. Universes with properties that have no analog in anything we experience or can imagine. Most physicists regard the Level 4 multiverse with skepticism. It is the point at which the program moves from physics into philosophy of a kind that may not be empirically accessible in any sense. If a mathematical structure exists as a physical reality but has no causal connection to our universe, if nothing in it can affect anything in ours, then what does it mean to say it exists? Whether this is a deep question about the nature of existence or an indication that the framework has lost contact with science is a debate that remains genuinely open. What is not debated is the elegance of the structure. Level 1, distant space with the same laws. Level 2, separate bubble universes with different constants. Level 3, quantum branches with every possible outcome. Level 4, every possible mathematics. Each level contains all the previous ones. Each is vastly larger than the last. The hierarchy is clean and systematic and, if you follow it honestly, deeply uncomfortable. The cosmological architecture. Let us now assemble the full picture. Because the individual levels of the multiverse are interesting on their own terms, but genuinely extraordinary when you see them nested together. You are sitting in a specific arrangement of matter, in a specific galaxy, in a specific region of the observable universe. The observable universe is the sphere of space from which light has had time to reach you. Beyond that sphere, extending outward in every direction, is the rest of our bubble universe. The Level 1 multiverse, vast beyond any meaningful description, containing in its full extent copies of every possible configuration of matter, including uncountably many identical copies of the observable universe and everyone in it. Our entire bubble universe is one of uncountably many bubble universes within the eternally inflating Level 2 multiverse. Each bubble nucleated from the inflating background at a different moment, settled into a different vacuum state, and contains a different set of physical laws. The great majority of them are sterile. A small fraction contain the right conditions for complexity. We are in one of the latter, and we are there because we can only exist there. Our bubble universe, with all its branching quantum history, is one node in the Level 3 multiverse. The quantum mechanical tree of all possible outcomes of all possible measurements throughout the universe's entire history. The branch we occupy is one among an effectively uncountable collection, each branch equally real in the mathematical structure of the wave function, each inhabited by observers who see exactly what the laws of physics in their branch lead them to see. And all of this, the Level 1, 2, and 3 multiverses combined, sits within the Level 4 structure of all mathematically consistent realities, of which our particular set of physical laws is one instance. The structure does not have a name that captures its scale. The word infinite is not adequate. A number followed by 100 zeros is not adequate. The full hierarchy of multiverses is a structure whose size cannot be compared to any quantity that has an intuitive meaning, because the most fundamental level, the Level 4 multiverse, is not defined by a size at all. It is defined by mathematical possibility, which is as large as logic permits and no larger. Somewhere in that structure, if any of this is real, is every possible version of every possible moment you could be experiencing right now. Every choice you have not made, every life you have not lived, every version of history that could have unfolded from any starting point, every universe that could exist, existing, the objections. The multiverse is not universally accepted. It is not even close to universally accepted, and the objections are serious enough that dismissing them is not an option. The first and most fundamental objection is empirical. Science, at its core, is a method for building knowledge through observation and experiment, a hypothesis that makes no testable predictions, a hypothesis that cannot, even in principle, be falsified, is not a scientific hypothesis in the usual sense. It may be a valid piece of mathematics. It may be a compelling piece of philosophy. But the scientific label comes with requirements. The other bubble universes in the Level 2 multiverse cannot be observed. They are separated from ours by eternally inflating space. No signal can cross from one to another. No experiment in our universe can detect the presence of another bubble. If our bubble collided with another early in its history, a possibility that some models permit, the collision might have left a detectable imprint on the cosmic microwave background. Physicists have searched for this signature. It has not been found. Its absence constrains the collision rate, but does not rule out the multiverse as a whole. The Level 3 multiverse is unobservable by definition. Different branches of the quantum wave function cannot interact with each other once decoherence has set in. There is no experiment that can detect the branch where you made a different choice, because any measurement you make in this branch produces a result consistent with this branch's history. The others leave no trace. The Level 4 multiverse is arguably unobservable by construction. A mathematical structure with no causal connection to ours cannot affect us or be affected by us. Its existence, if it exists, is logically and physically isolated from anything we can probe. This is a genuine problem, and physicists like George Ellis and Joe Silk have argued forcefully that the uncritical acceptance of multiverse theories as scientific represents a retreat from the empirical standards that made physics great. Their concern is not about the mathematics or the philosophy. Their concern is about the sociology of a field where ideas can become widely accepted without the discipline of testability. The defenders of multiverse theories have responses. Lee Smolin points out that many well-accepted scientific frameworks, the interior of black holes, the earliest moments of the Big Bang, describe regions that are empirically inaccessible but are not therefore considered unscientific. The Standard Model makes predictions about conditions we cannot replicate in the laboratory. The criterion of testability applies to the framework as a whole, not to every individual prediction. Tegmark argues that parsimony cuts the other way. The quantum mechanical wave function, which no serious physicist doubts, describes all branches equally. Assuming that only one branch is real adds an extra postulate, wave function collapse, that the mathematics does not require. The many worlds interpretation, for all its extravagance in branches, is actually more parsimonious in its mathematical assumptions. David Deutsch argues that the multiverse is not an additional hypothesis layered on top of quantum mechanics. It is what quantum mechanics says. Reading the theory and not concluding that the other branches are real is, in his view, like reading general relativity and declining to believe that black holes exist because they are hard to visit. The Anthropic trap. There is one objection to the multiverse that deserves its own section because it is subtler than the others and more difficult to answer cleanly. The anthropic principle, in its weakest form, is a tautology. We can only observe the universe from a position compatible with our existence. Any universe we observe must be one in which observers like us can exist. This is not a theory about the universe. It is a selection effect. Of course, the universe we live in is compatible with our existence. We could not be here to observe an incompatible one. Applied to the multiverse, the anthropic principle says, among all the bubble universes in the Level 2 landscape, we inevitably find ourselves in one with the right conditions for life, because only in such universes can anyone find themselves anywhere. This explanation is valid as far as it goes, but it goes less far than it might appear to. The anthropic principle, applied to the multiverse, can explain why we find ourselves in a universe compatible with life. It cannot, by itself, predict what kind of life-compatible universe we should find ourselves in. It cannot tell us whether we should expect to be in a universe with our specific cosmological constant, or our specific number of spatial dimensions, or our specific particle masses. To make those predictions, you need a probability distribution over the multiverse, a theory of how likely each possible vacuum state is to nucleate and how likely it is to produce observers. No such theory currently exists. The measure problem, the question of how to assign probabilities to different bubbles in an eternally inflating multiverse. is one of the deepest and most stubbornly unsolved problems in theoretical cosmology. Without a solution, the anthropic multiverse can explain why we are in some life-compatible universe, but it cannot predict which one or tell us whether our specific fine-tuned values are expected or surprising within the broader landscape. Steven Weinberg achieved a partial success in 1987 when he predicted the order of magnitude of the cosmological constant, using an anthropic argument before the accelerating expansion of the universe had been measured. He argued that the cosmological constant could not be much larger than its observed value without preventing galaxy formation, and therefore observers like us could only exist if it were roughly in the observed range. The subsequent discovery that the cosmological constant is indeed in that range, confirmed in 1998, was widely cited as an anthropic prediction confirmed by observation. But even this success is contested. The predicted range is large, and the actual value sits in the lower part of it. Whether the anthropic framework predicted the specific value or merely constrained it to a range that turned out to contain the right answer is debated. And the measure problem means that even this partial success cannot be straightforwardly extended to other constants. The anthropic multiverse is a serious scientific idea. It is also an idea with a fundamental unsolved problem at its core, and honest defenders of the framework acknowledge both. What the multiverse does to the self. There is a consequence of the many worlds multiverse that most discussions of it mention, and very few sit with long enough to feel the weight of. If every quantum measurement branches the universe into parallel copies, and if quantum events underlie essentially all physical processes at the microscopic scale, then the number of copies of you in existence right now is not a large number. It is a number that grows without bound at every moment, in every direction. Every photon that entered your eye in the last second contributed to a branching. Every neuron that fired in your brain did so as the result of processes with quantum-level contingencies. Every breath you drew involved molecular collisions with quantum outcomes. The number of branches that have split off from the single moment before this one is incomprehensibly large. And in all of those branches, there is a person, made of the same atoms, carrying the same memories with the same sense of being a continuous self, who has just had a slightly different experience. Most of those differences are too small to notice. Some are not. In some branches, the quantum fluctuations that preceded certain decisions, the ones that feel from the inside, like free choices, resolved differently, and you made a different choice, and your life proceeded along a different path. In some of those branches, the differences compounded. In some of them, the life you are not living right now is very different from the one you are. What does this mean for personal identity? Are all those copies you? They have your memories. They believe they are you. They have the same history up to the point of divergence. The sense of continuous self that you carry through time is, on every account we have of consciousness, narrative construction. A story the brain tells about a sequence of experiences. Every branch carries that narrative intact, right up at the moment of divergence. This question does not have a settled answer in philosophy, and the emergence of the many worlds interpretation has made it considerably more urgent. Whether it is a question that physics can address, or a question that requires a theory of consciousness that we do not yet have, is itself unsettled. What is not unsettled is the structure of the argument. If many worlds is correct, then the question of identity across branches is not a philosophical curiosity. It is a real question about real physical objects. The branches are as physical as the one you are in. The copies are as real as you are. The question of what you means in that context is one that the physics cannot currently avoid and cannot currently answer. The landscape and the laboratory. For all the philosophical turbulence of the multiverse, it has not been without experimental consequence. The same physics that predicts the multiverse makes predictions about our own universe that are, in principle, testable. Eternal inflation, for instance, predicts specific statistical properties of the density fluctuations in the cosmic microwave background. The pattern of hot and cold spots in the CMB is determined by the quantum fluctuations of the inflaton field during inflation, amplified to cosmic scale by the rapid expansion. Different inflationary models predict different patterns. The measurements by the WMAP satellite and then by the Planck satellite have confirmed the broad statistical features predicted by the simplest inflationary models with remarkable precision. This does not confirm eternal inflation specifically, or the multiverse it implies, but it confirms the inflationary framework that gives rise to eternal inflation as its natural extension, and the consistency is significant. Bubble collisions. The possibility that our universe collided with another bubble universe early in its history would leave a specific and detectable imprint in the CMB, a circular disk of anomalous temperature with a specific profile of variation from center to edge. Searches for this signature have been conducted and have not found a confirmed signal. The absence constrains the rate of collisions but does not rule out the multiverse. If no collision occurred, no signal would be expected regardless. String theory, which provides the landscape of vacua that underlies the Level 2 multiverse, makes predictions about particle physics that are, in principle, testable at collider energies. The predictions are not specific enough in their current form to be decisive tests of the string landscape. But the framework generates predictions about supersymmetric particles, about extra dimensions, about the behavior of gravity at short distances, that current and future collider experiments can probe. The Large Hadron Collider has not found supersymmetric particles in the mass ranges where some models predicted them. This is a constraint on those specific models, not on string theory as a whole or on the landscape framework. But the non-detections have complicated the theoretical landscape in ways that are themselves informative. The relationship between the multiverse and experimental physics is not one of clean prediction and clean confirmation. It is one of indirect consistency checks, constraints, and the slow accumulation of evidence that either supports or undermines the frameworks from which the multiverse emerges. It is not the kind of evidence that proves the multiverse exists. It is not the kind that rules it out. The situation is, as in all honest frontier science, genuinely uncertain. What we do not know. The honest accounting of the multiverse has open questions at every level, and they deserve plain acknowledgement. We do not know whether eternal inflation occurred. Inflation itself is strongly supported by observations of the cosmic microwave background. But whether it is eternal, whether it continues outside our bubble, generating more bubble universes at every moment, depends on the specific dynamics of the inflaton field, which are not directly observable. Eternal inflation is the natural consequence of many inflationary models, but not all, and the distinction cannot currently be tested. We do not know whether the string theory landscape is the correct description of the space of possible vacuum states. String theory is the most extensively developed candidate for a unified theory of quantum gravity, but it has not made confirmed predictions that distinguish it from other frameworks. The landscape of 10 to the 500 vacua is a feature of string theory, not a confirmed feature of nature. We do not know how to solve the measure problem without a theory of how to assign probabilities to different regions of the multiverse. The anthropic principle cannot be turned into a predictive tool. It remains a selection argument rather than a scientific theory in the full predictive sense. We do not know which interpretation of quantum mechanics is correct. Many worlds is the most popular single interpretation among working physicists, but it falls short of consensus. The measurement problem remains genuinely unsolved. The alternatives, Copenhagen, pilot wave, relational, cubism, each resolve the problem differently and each faces its own difficulties. We do not know what the multiverse implies for probability. If there are infinitely many copies of you making every possible decision, what does it mean to say that a choice has a specific probability? The Born rule, the quantum mechanical rule for calculating probabilities, needs to be derived from the many-world structure, and several proposals exist, but no derivation commends universal agreement. And we do not know, at the deepest level, whether the level 4 multiverse, the mathematical multiverse, is a scientific hypothesis, a philosophical one, or a category error. Whether mathematical existence and physical existence are the same thing is a question that sits at the boundary of physics, mathematics, and metaphysics, and there is no agreed method for answering it. The architecture is clear. The foundations are still being excavated. Every possible you. Hugh Everett III sat in his Princeton library carrel in 1954, surrounded by his calculations, and followed them to their conclusion. He did not find what he was looking for. He was looking for a solution to the measurement problem. He found instead a structure so large that the measurement problem was dissolved inside it the way a grain of salt dissolves in an ocean. The wave function never collapses. Everything that can happen does happen. The universe branches endlessly in every direction at every moment, and has been doing so since the first quantum event in the first microsecond of the Big Bang. Whether he was right is still not known. Whether the branches are real is still contested. Whether the other levels of the multiverse, the distant regions, the other bubble universes, the mathematically different realities, exist alongside our own is a question that the physics has opened but not yet answered. What is known is that the question is serious, that it is taken seriously by serious physicists with serious mathematics behind them, that the evidence for inflation, the mechanism that most naturally gives rise to the level 2 multiverse, is genuine and substantial, that the quantum mechanics behind the level 3 multiverse is the most precisely tested theory in the history of science, that the mathematical structure of the level 4 multiverse whatever its physical status, is logically coherent and philosophically rich. The architecture of the multiverse, if it exists, is the largest structure that human thought has ever attempted to describe. Larger than the observable universe by factors that have no intuitive meaning. Larger than any physical infinity, because it encompasses mathematical possibility itself. It is a structure in which every story that can be told is told, somewhere. Every life that can be lived is lived. Every physics that can operate does operate, in some region of some level of the hierarchy. And you? A specific arrangement of matter and energy and memory at a specific location in a specific branch of a specific bubble universe at a specific level of an architecture that may or may not have an end. You are one instance of all of that. One reading, one realization, one version of a pattern that may be playing out in every possible variation simultaneously. Now, I asked you at the start of this video to tell me which version of reality you are in right now. Warm or cold? Morning or evening? Coffee in hand or already done? Here is what I actually want to know. When you think about the possibility that in some branch of the quantum multiverse, in some bubble across the inflationary landscape, in some other mathematical structure entirely, a version of you made every choice you did not make, took every road you passed, said every word you held back. Does that feel like freedom or like loss? Drop your answer in the comments. Tell me where you are, what time it is there, whether the sky outside is light or dark, and what you genuinely think about what you just heard. I want to see how many different corners of this one universe, the only one any of us can be certain of, are wrestling with the same question at the same time. The multiverse may or may not be real. This conversation is. You've been watching the entire history of the universe. Don't forget to like and subscribe, and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.